Use P of t to represent the amount. The total for the first 4 years, so it's 8.5% interest. I mean, initial deposit of 5,000. This would be the initial value problem. Now we just have to solve it. That's linear, right? That would be our integrating factor. And just anti-differentiate both sides. P of t is CE to the 0.085 t. P of 0 would just be C, right? And that has to be 5,000. And so for the first 4 years, we're modeled with 5,000 e to 0.085 t. However, we have a different interest rate for the last 3 years. It's 9.25%, right? Our initial value I'm going to call that something different. That piece of one distinguished from my other model. The initial value is P of 4. Because they have the, once the next 3 years starts, how much is in the account? P of 4. I'm going to leave it at P of 4. And notice I'm also not writing P sub 1 of 0. T doesn't start at 0, so I guess I could write P sub 1. Five would be the initial condition. Starts the 5th year, right? Would it? I don't know. Would be 4. 5 would represent after 5 years. 4 in this case would represent the 0 start of the 5th year. Now we just solve this. Solve, that's what you should get. Right? And then P1 of 4. I had to start at 0. I adjust for that later. I'm starting at 0. Gives me just the C1, which I want. I could use the 4. It's going to make it a little bit messier. And that has to equal P of 4. 5,000 E 0.085 times 4. It's 0.34. 0.08 times 4 would be 0.32. 0.005 times 4 is 2, or 0.02. That's C1. And when you multiply, same base, you add the exponents, right? Question. That would go from 0 to 3. If we adjust this, what we can do is write this model. It's a piecewise function, right? That piece was the first 4 years. The second piece is going to start just after t equals 4. We added 4 to the domain, right? That means we're shifting to the right 4 units along the t-axis. T gets replaced then with t minus 4. As I said, I could have actually kept here 4, because the t minus 4, you would have seen where that minus 4 comes in. You would divide it by that number times 4. I'm just saying subtracting 4. Just easier to do it that way. There's the model. Well, technically, it says for the last years. So I guess I could say this just continues on forever. So I could say just for this. I'm doing last 3 years because I think it asks for 7, right? But it's for the last years, it just always be, just keep increasing. Here, 7, you're just going to plug that in, that second piece. What do you get? Oh, the whole thing.
Oh, sorry. I'm sorry. $9,271.43.
Almost doubled. Right. So it is possible that you will have to break your problem up into pieces. I'm going to have time to do this one more. Population. So population of the country increasing rate proportional to the number of people in the country. but N of T represent that number. 2 years population doubles, 3 years population is 20,000. You want to estimate the number of people initially living. So rate of change is proportional to the number of people in the country. The NDT is some constant times n. And our initial condition, n of 0, is n naught. We'll call it n naught. I'm not going to go through all of the work again. It's going to solve the n of t as c e to the kt. Using the initial condition, c is n naught. Took 2 years to double. N naught e to the 2k has to be 2 times n naught. E to the 2k is just simply 2. We need to solve for k, that constant proportionality. Shouldn't be too difficult. It's a half log of 2. Replace that with, replace k up here with that. N naught times 2 to the t over 2. That is our model. We also know that after 3 years, the population is 20,000. Now you can use the solve for n naught. No, that's not right. That's right. 20,000 times 2 to the negative 3 halves. What do you get? That can't be right. 20,000 is less than that.
The negative, sorry. $7,071.
Why'd you round it to the nearest whole number?
Because it's people.
Can't really have a fraction of a person. Huh? Well, if you consider a person who's born with a missing arm, technically I guess you could say that's not really a whole person. That'd be a fractional person, but I don't think we'd be that evil, would we? So it depends on what we do, how we define fraction of the person. So initially, guess is probably about 7,000. Do we know that for sure? No, but that's what the model predicts. The only difference now with models is that you actually have to set it up first, but then solving it is the same. So part of that is obviously the setup. As with all word problems, just take practice, right? You have to read the problem, identify what you're given, identify what you want to solve, set up your model, and go from there. That finishes up first order differential equation. So get into your groups. Did you get a reference sheet for the exam? So make sure you get that for you.
No, I would ask.
Let's say 30 minutes. By then, 7-minute exam, 7-minute break. We'll start up again at 2 o'clock. We'll start with the theory behind higher order linear differential equations. There's going to be a lot of reading in this section. So read through the slides. This is the preliminary theory. I also introduced matrices for those who haven't had linear algebra yet. Matrix is just an array. Rows and columns. Matrices are equal if they have the same size and all corresponding entries are the same. Summing up two matrices, you just add corresponding components together. So corresponding entries added together, that's the sum of two matrices. Scalar multiple, you just multiply each entry by the scalar. Transpose, rows become columns, columns become rows. I don't think we actually need to use the transpose for this course. The product of matrices sucks. So something to note, when you add matrices, they have to be the same size. When you multiply matrices, order now matters. You've lost commutativity. The number of columns of the first matrix has to be the same as the number of rows of the second matrix. Otherwise, the product doesn't exist. And the dimension of the new result, rows of the first matrix by columns of the second matrix. Right, so A is n by n, B is n by p, that does exist, that product does exist. A times B will be n by p. Each entry of your product, it's easiest to think of it in terms of doing dot products. You take the first, so I'm going to look at the 1, 1 entry. Take the first row of the first matrix, the first column of the second matrix, treat them like vectors and dot them. That's the entry. And you have to do that for every single entry in the matrix, in the product. So if it's a 10 by 10 product, that's 100 entries you have. That'd be 100 dot products. Yeah, chances are, not just chances, I can guarantee you that when we actually get to need to use this, identity matrix, one's along the main diagonal, zero's out the rows. You can have non-singular matrices. Non-singular means it has an inverse. An inverse is a matrix such that A times A inverse is the identity matrix. And A inverse times A is also the identity of the appropriate size. A is non-singular if and only if its determinant is not equal to 0. Yeah. That's the method for finding inverses. One of. I'm not worried about the row reduction just yet. I'll deal with that when we look at linear systems. So for now, we're going to use this method. 1 over the determinant times the, what's that called? Oh, the adjoint. 1 over the determinant of A times the adjoint of A. Again, I'm just going to be using technology to find the inverse. You can differentiate matrices, and you can integrate matrices. No one ever said that a matrix, each entry of a matrix has to be a constant. Entries of matrix can be functions, and thus subject to change. Linear algebra actually, I think linear algebra only deals with elementary linear algebra is only going to deal with the matrices where the entries are constant. But that's not always true. But it's differentiating, integrating. It's not that difficult. You just differentiate, integrate each entry. And again, I'm just going to be really using technology when we get there. It's just kind of setting the groundwork for it. Nth order, this really should be linear initial value problem. It's right there. Okay, for linear differential equation. That form. Notice, if it's nth order, you have up to the n minus first derivative in the initial values, and they're all of the same point. Right? So y is 0, y prime is 0, y double prime is 0, y triple prime is 0, and so forth. I think that's the existence and uniqueness theorem. Boundary value problems. Yeah, these suck. These are what are known as your boundary conditions. One of the simplest boundary conditions could be, if you look here, these are not all the same one. That would then be a boundary condition. Or if you're looking at a wire, I think that would be a first order differential equation. I would give you the condition on y at one endpoint and on the other endpoint. Those are boundary. Those are the boundary values. But that's not how they have to be. Right? in general, anything of this form would be boundary conditions. And in general, boundary value problems are very difficult to solve. So we will really not be doing boundary value problems. If we do, they're really simple. All right, homogeneous versus non-homogeneous. If what it equals, your g of x, is identically 0, that is called a homogeneous equation. If it's not 0, then it's non-homogeneous. The idea of a differential operator, I don't really think we're going to be worrying about that. I used to do an annihilator approach as well, but I think I got rid of that. Superposition for homogeneous equations. If you have a set of solutions, y1 through yk column, then any linear combination of those solutions is also a solution. Again, I'll let you read it. Set of functions linearly dependent if there exists constants, not all of which are 0, so that linear combination is 0. They would be linearly independent if the only solution is the trivial solution. This brings in the Wronskian, which is a test on whether functions are linearly dependent. So we define the Wronskian of a set of functions to be this determinant. And so if you have two functions, it's a 2 by 2 determinant, right? First row is just the functions, second row are the derivatives. 4 functions would be 4 by 4. Right? The functions, derivative, first, second, third. So on and so forth. This is the test. That set of solutions is linearly independent if and only if the Wronskian is not equal to 0 for every x in the interval. We would call such a set of functions a fundamental set of solutions. So if you have a set of solutions that are linearly independent, we call that the fundamental set. I think that's the existence theorem for the existence theorem for a fundamental set. It's just saying that every homogeneous nth order linear differential equation has a fundamental set. General solution, linear combination of the fundamental set. Right, so you want to find each of those solutions. There will be n of them if it's nth order. And then you just write out the linear combination. Every linear combination, right, is a general solution. Remember, because it's a family of solutions. You can find those constants if you're given either initial conditions or boundary conditions. Again. Any function that satisfies the non-homogeneous equation is said to be a particular solution. Then the general solution of a non-homogeneous is the general solution of its homogeneous part. We call it the complementary function plus the particular solution. So when we go to solve these types of equations, we first look at non-homogeneous, the homogeneous case. Then we move on to the non-homogeneous. Because solving non-homogeneous, you have to solve the homogeneous first. And then there's two methods that I'm going to look at to find a particular solution. And then your general solution just be the sum of those two functions. And I actually just mentioned that that's called complementary function. Superposition for non-homogeneous. If you have a set of particular solutions, then their sum is also a particular solution. Reduction of order. So let's say you have a non-trivial solution and you seek a second solution that is linearly independent. This is the method you can use. So this is only breaking it down for a second order, but in general, this can be extended. This is, is it Bell? I think that's how it's pronounced. Bell's formula. Double check that. I didn't call it that in this book. What is in here? That's nice. Yes, it is. Okay. No, so that was something different. Has to deal with Wronskian. I think I used that actually. Yes. And so that's reduction of order. That would be your second solution from the first solution. There's also a method known as a Bell's formula to find a second solution. Pretty sure because it involves the Wronskians. That's theorem 514. Okay, just want to take your textbook. And that uses Cramer's rule. I'm going to stick with essentially doing linear algebra. Because everything else is either theory doing what we've already done, verifying it's a solution and finding the constants. You know, folks, I'm working with matrices here. Given two matrices, find A plus B, 2A minus 3B. First thing you generally want to do is decide, is the operation even defined? So is A plus B even defined? To be defined, they have to be the same size. They are both 2 by 3. And 2 rows, 3 columns. So yes, it is defined. Then A plus B has the same size. It's 2 by 3. Each entry in this matrix will be the sum of corresponding entries. Right? So the first entry, don't say first entry, the 1, 1 entry is the sum of the 1, 1 entries of A and B. 1 plus 3. That'll be negative 2 plus 0, 3 plus 2. There's your first row. Right, nothing too difficult. 4 plus negative 7, 5 plus 1, negative 6 plus 8. There's A plus B. Two A minus 3B. First, some trivia. You may have come up with this in Calc 3, so you can't answer. How many operations are there? How many arithmetic operations are there?
4.
What are they?
Addition, subtraction, multiplication, and division.
Right? You were lied to. There are not 4 operations. There's 2. Subtraction and division are not actually operations in mathematics. When we say subtraction, what we actually mean is sum of the additive inverse. When we say division, what we actually mean is multiplication of the multiplicative inverse. That is extremely important to remember in theory. You do not have division. You do not have subtraction. So if you notice when we went over the matrix operations, there wasn't an A divided by B. This is also why, by the way, when you do the order of operations, you're taught that you do what? You group multiplication, division together, and you group addition, subtraction together. Right? They don't say do all the multiplication first, then all the division. It's you do multiplication and division as it appears left to right, because it is the same operation. Same thing with addition, subtraction. So there's your trivia knowledge for the day. Which means when we're doing 2a minus 3b, what we're actually doing is 2a plus negative 3 times b. With scalar multiplication, size of the matrix doesn't matter. Find 2a first. You just multiply every entry in a by 2. Right, there's 2a. Negative 3b, multiply every entry in b by minus 3. Look at those two matrices. Do they have the same size? Then the sum is defined. 2 plus negative 9. Negative 4 plus 0. 6 plus negative 6. 8 plus 21. 10 plus negative 3. Negative 12 plus negative 24. Good. This is like the first day of linear algebra. Given two matrices A and B, we're going to find A times B. First, we have to decide, is the operation even defined? Do you want to mention? Addition of matrices is commutative, so that order doesn't matter. You only lose commutativity with multiplication. What's the size of A? What's the size of B? Number of columns of A. Does it match the number of rows of B? Yes. A times B is defined. What will the size of A times B be? 2 by 4. Again, I'm just going to do this by hand for now, just so we see how it's going. Start with the 1-1 entry. You want row 1, column 1. Treat those like vectors and take their dot product, which is multiply corresponding components and add. 2 times 2, 4. 3 times 1, 3. 4 plus 3 is 7. Negative 1 times 4, negative 4. Plus 7 is 3. There's your 1, 1 entry, 3. And you have to do that for all 8 entries. Let's just go by column. Want the 2, 1 entry? So we just take row 2, column 1, and then it's the same procedure. 4 times 2 is 8. Negative 2 times 1 is negative 2. Plus 8 is 6. 5 times 4 is 20. Plus 6 is 26. Negative 2, 9 is 7. Minus 1 is 6. Negative 4 minus 6, negative 10. Plus 5 is negative 5. We're now halfway done. Oh, that's zeros. Negative 15 plus 2 is negative 13. Oh, yes. 10 minus 10. $12 plus 3, 15. 15 minus 2. And the last entry, 24 minus 2 is 22. Plus 10 is 32. There's the product. It's not difficult. It's just tedious. And those are small matrices. Those are very small matrices that we're trying to get. General activity, I did 10 by 10. No, it's string theory, I'm sorry. General activity 4 by 4s. And you have tensors. Again, even those are pretty small. String theory, 10 by 10 matrices. Yeah, it's pretty hideous. Used to be 26 by 26. Thankfully, we reduced the dimensions down to 9. Inventory can also be done in terms of matrices. So you set up essentially the search algorithm is an array. So matrices are used quite a bit, especially in comp sci. Determinants. There are 3 ways of taking a determinant. First way is to use the definition of a determinant, which I did not give for a reason. That is very theoretical heavy. Save that for an actual linear algebra course. You can use the definition to simplify derivatives, determinants of 2 by 2 and 3 by 3 only. That's the method. I'm going to use that method for this first problem. I think I have 3 total. I do. 1 for each of the methods I'm going to use. Oh, actually, sorry. I can only do 2 methods right now. The third method, so the first method is just to use the definition. Second method is to use what's called cofactor expansion, which if you've done cross products, you're familiar with. The third method is known as triangulation. You essentially use row operations. The idea is you want to get into a triangular matrix. Each operation that you use has an effect on the determinant, so you have to keep track of that. And then the determinant of a triangular matrix is just the product of the diagonal. I didn't do row operations yet. There's a reason for that. I don't want you to forget it when we look for eigenvalues. So I'm going to do it when we look at systems of linear equations. So for now, we only have 2 methods. The definition and cofactor expansion. We use the definition here. Here's what we do. Copy the first 2 columns and paste them after the third column. Take the sum of those products. What I'm going to do is, just for now, do each product individually. The 2 times 6 times 1. 3 times 7 times 8. 21 times 8 is what, 168? Oh, okay, I actually did a different method in here. That's okay. 4 times 5 times 9 is 180. Now go the other direction. These will all be multiplied by -1. 4 times 6 times 8. 48 times 4. 192. 2 times 7 times 9. 7 9 63 times 2 126. 3 times 5 times 1. Your determinant is that sum. Now, can I do this without a calculator? Yes, I can. 12 and 180 is 192 minus 192 is 0. Perfect. 126 and 15. 141. So 168 minus 141. Well, 168 minus 100 would be 68. Minus 40 is 28. Minus 1, 27. There's your determinant. Oh, by the way, would that matrix be invertible? Yeah, it has a non-zero determinant, so that matrix has an inverse. Something to note about determinants, you can only take the determinant of a square matrix. And a square matrix is a matrix whose rows and columns are the same. They have the same number of rows and columns. So that is the shortcut that you can get just from using the definition. And that only works for 3 by 3. 2 by 2 is a different method. I'll show that off later. But this method of copy and pasting doesn't work for 4 by 4 or 5 by 5. It only works for 3 by 3. Speaking of 4 by 4, since you don't know the definition, I mean, if you did, you probably wouldn't want to use it anyway. It's going to have. Okay. So, how many terms were in that sum? How many terms are there? 6. Huh? Okay, I don't care. I'll look it away. I'll tell you, for 2 by 2, using the definition, you have 2 terms in the sum. So how many terms do you think is going to be in a 4 by 4? So 2 by 2 had 2, 3 by 3 had 6. How much is in a 4 by 4?
16.
24. How many terms will be in a 5 by 5? What is it?
1.5.
Close. 120. 5 factorial. Number of terms using the definition is the size of the matrix and factorial. Right there, 5 by 5, the definition is not really practical to use. 10 by 10, 10 factorial. That's a really large number. I think that's over 1 million, if I remember correctly. Well over 1 million. I think it's like 7 million or something like that. That's where you want to use one of these other methods. Using cofactor expansion is the only other method I have right now. Cofactor expansion actually is not the best method. Reduction to triangular form is the best, but we don't have that yet. Here's how cofactor expansion works. Pick a row or a column. That's the one that you're expanding across. It doesn't matter. You can use any row or any column. We can use that row. Take a guess why? It has 2 zeros in it. Start there. The absolute value just means determinant when you deal with matrices. So the first thing we have to do is determine what entry is that. It's the 3, 1 entry. What's 3 plus 1? It's even. Negative 1 to the 4 is positive 1. So it states with a sign. That was the 3-1 entry. So you cross out column 1, row 3. What you're left with is a 3x3 matrix.
But you take out the 3 again, just because?
That's the method of cofactor expansion.
Oh, you can take out the first number of the row.
Well, that is the method of cofactor expansion.
Okay.
And we have to do that for every single entry in that row or column. This whole thing is the cofactor. This determinant is called the minor. Next entry is 0. Oh, that's nice. It would be negative though, right? Because that's the 3-2 entry. But since it's 0, it goes away, so we don't care about it. Right, I think I'll write it out anyway. Just to get you the idea of what we're actually doing. Right, so now you cross off second column, third row. And it's the determinant of the new matrix. Next entry is the 3-3. 3 plus 3 is even. Now you cross off row 3, column 3. That determinant. Next one is 3-4. 3 plus 4 is 7, so it's minus the entry times determinant, cross off row 3, column 4. So what cofactor expansion does is it takes that 4x4 determinant and reduces it to 4 3x3 determinants. In this case, we reduce it even further with clever choice of the row. But now you have 3x3 determinants. If you're to use cofactor expansion again, each of those 3x3s becomes 3 2x2s. So let's see why this method isn't actually the best method. Right, each of those becomes 3 2x2, so that's now 12 2x2s you have to do. Now imagine 5x5. It's 5 4x4s. Each 4x4 is 4 3x3s. And each 3x3 is 3 2x2s. That's what 5 times 4 times 3. That's 60. Which you can reduce with clever eggs. So again, not really the best method, but certainly better than 120. I'm not going to use cofactor expansion with 3x3s because they're pretty easy to take. And those two go to 0. Now just use the method I introduced previously for the 3 by 3. What you should get is that first determinant. It's 14. Then that second determinant, you should get 250. Determinant is 2042. Bummer! That's not triangular. So close. No, we'll find out. Right matrix. Yes. Yeah, maybe triangle, I think, with those two. Brett's going to change that value. Let's see how it worked. Cofactor expansion. The idea is you want to pick a convenient row or column. I see a really convenient choice. Which one?
Column.
Yeah. Look at all those zeros. We're only going to have one 4x4 determinant to worry about. 5. What entry is that? Is that going to be a positive or negative? Oops. That. Now we have to use cofactor expansion again. There's several choices we can use. But there is one convenient choice. Which is the most convenient choice?
That's true.
row 4 has 2 zeros and the constants are 1s. Well, plus minus, but that's irrelevant. That first one, the 1, what entry is that? For what? 4 plus 3 is what?
Oh, sorry. 7.
Which is odd. It's going to be multiplied by -1. That's 1 times the determinant. Two, 1, -6. 1, 2, 1. 0, 0, 6. Then you have the 4, 4 entry, right? 4 plus 4 is 8. So it's a plus. And the entry itself is -1. Now the determinant. 2, 1, 1. 1, 2, 1, 0, 0, 3. And then if you wanted to, you could use cofactor expansion a 3rd time.
Why is the 5 not negative? The first 5? And the first
What entry is the 5?
1, 1.
1, 1. 1 plus 1
okay.
is 2. So if you sum the row number and column number it's in, if it's even, the sign of the entry stays the same. If it's odd, the sign of the entry switches. Right, again, you could use cofactor expansion again. They both have row 3, 2 zeros in it, so it wouldn't be too terrible. Or you could just use the method for 3 by 3, it doesn't matter. And either way, I did the method. I factored out a negative. That first determinant, you should get to be 18. Second determinant, you should get to be 9. 18 and 9. What is it?
27.
Times 5. 135, and then there's a negative. Determines negative 135. By the way, with the use of cofactor expansion, it should be really easy to prove that if a matrix contains a row or a column that consists entirely of zeros, its determinant is 0. Using the other method, combined with that observation, you also find that if 2 rows or columns of a matrix are identical, or actually, in elementary linear algebra, you only do row operations, not column operations. So it's really if you have 2 identical rows, the determinant is 0, or if one row is a scalar multiple of another row, its determinant is 0. But you can say the same thing for columns, because there are column operations as well. Again, that is just a real quick introduction to matrices. There's still more to cover on matrices, actually a lot more to cover on matrices. I'll leave most of that for the linear algebra course. There's just one other thing I do want to look at, and that I was saying is row reduction for operations. We'll do that a little bit later. So for now, that's kind of like the basics of a matrix. And really, that's all just to understand the theory. We're never actually going to be using this in terms of solving an equation. But the Wronskian, the Wronskian is, of course, determinants. And that's just to verify that it's a fundamental set. Well, the method I'm going to be using to solve differential equations, it's proven that that method always forms a fundamental set. And it uses, obviously, the Wronskian. So it won't even be taking Wronskians in general. We will, however, use linear algebra when we have to do systems of linear equations. But for now, this will just help you understand the theory. Good question. Next class will be starting off with just the worksheet on the theory. I think it's going to ask you to prove fundamental sets. So you have to calculate Wronskian. I think it also is going to involve like, here's the differential equation, here's solutions to it. Verify it's a solution. And then find your initial conditions, find the constants. So stuff like that, you're not actually going to be solving anything. After that will be the review worksheet for the first exam. So we're not learning anything new next time. The extra credit is also posted. So you have a chance to earn 6 points on the first exam. So what you're going to do is with the exercise asks you to do, it's the same as Calc 3. You're going to use AI to create a 20-question quiz on the topics, along with solutions. You will then take the quiz yourself, compare your solutions to what AI said the solutions are, note any errors, explain the errors, right? That's all part of the reflection. You write up a reflection on it. So it's both good review and to show you the use of AI, as well as any pitfalls. AI is generally pretty good though. It's gotten really good with that. I might be able to find any errors anymore, if you actually prompt it correctly. But I'm telling you to do that because that's part of the assignment. And that's, like I said, for an additional 6 bonus points on the first exam. I'll actually use the rest of this time to finish up that first worksheet if you want. Otherwise, I'm done. Don't forget, the homework journal is due the day of the exam. Oh yeah, your first group assignment is also coming due. And then your reference sheet, as a reminder, just don't forget that. Right, and yes, because you had that issue last class, LA 129 is a collaboration room and it is open. It is always open. So, because I have to kick you out here because I have to lock the classroom when I leave. But if you want to work in groups, Student Center has a bunch of collaboration rooms, and this building I know has at least one for sure, LA 129. That is always unlocked for students.